Welcome back, student. Let's take example on this multi-stage compression process. Let's take example on numerical. A single acting two-stage air compressor deals with 4 meter cube per minute of air. So the initial condition of volume for two-stage air compressor, that is given 4 meter cube per minute of air at 1.013. This is the initial pressure is given, and 15 degrees centigrade. So 15 degrees centigrade, and the temperature is also given, that is 15 degrees centigrade, with a speed of, that means basically two-stage when it is two-stage compression, there will be low pressure cylinder and high pressure cylinder, and with a speed of 250 rpm. The speed is given. Now delivery pressure, so final delivery pressure, that will be P3's value is given, that is 80 bar. So P1 1.013 bar, P3 is 80 bar is given. Okay, assume complete intercooling, means intercooling process takes place perfectly, perfect intercooling takes place. Now you have to find the minimum power required by the compressor. This is the first part of the numerical. You have to calculate on that. And the bore and the stroke of the compressor. Bore means the diameter. So, okay, bore means diameter of the cylinder, and stroke means length of the cylinder or compressor. Okay, assume the piston speed is 3 meter per second and mechanical efficiency is given 75, volumetric efficiency given. Now first stage of polytropic compression process. Now first of all, you have to, as you know that to get the maximum efficiency, the main condition is that the P2, that intermediate pressure, basically equal to the under root of product of initial pressure and final delivery pressure. So P2 will be under root of P1, P3. The value of P1 is already known to you, that 1.013 bar, and P3 is 80 bar. Okay, here it is 1.013 bar and 80 bar. So P2 will be 9 bar. Okay, now as we know that mechanical efficiency, now mechanical efficiency is basically defined that indicated power of the compressor divided by power input. Indicated power of compressor divided by power input. Now power required for the compressor, so power required for the compressor means what is the power input actually? That power input, that will be indicated power input into 1 by mechanical efficiency. Okay, so from this expression you have to calculate the what is the power required to input for the compressor. This is the power required for the compressor, that is equal to indicated power of the compressor into 1 by mechanical efficiency. So this term is basically defined, this expression, that indicated power of the compressors and 1 by mechanical efficiency. Okay, now 2 into n, because the compression process takes place, that value of n that is given, that follows PV to the power 1.25 is equal to constant. So value of n will be 1.25 here, and 1.25 minus 1, that will be minus 25 with the 0.25 into initial pressure, that is given value, that is 1.013 bar into 100, it is converted into kilo Pascal, and divided by that 0.75. What is 0.75? Because of mechanical efficiency is given that 75%. Now this mechanical efficiency is given as 75%. This mechanical efficiency given as 75%. So this mechanical efficiency divided by 0.75 into V1. Value of V1 means volume. Volume, that is given 4 meter cube per minute. 4 meter cube per minute. So you just convert into per second. So 4 by 60. Okay. Into P2 by P1. P2 value is 9 here. So this, from this equation, so this is 9. P1 is given, that you already know, that 1.013 to the power n 0.25 divided to 1.25 minus of 1. So ultimately the power required for the compressor, the answer will be 49.34 kilowatt. 49.34 kilowatt. Okay. And the second part of the numerical, that the bore and the stroke of the compressor. You have to calculate the bore and stroke. So bore and stroke means the length of the piston that can be traveled from top dead center to bottom dead center, that will be calculated. That stroke, as it is, when you calculate the stroke and the value of the piston speed, that is given 3 meter per second. So 3 meter per second, that means the piston can travel with some speed, that speed is given, that is 3 meter per second, and that is, as it is two-stage of compression process, the two-stage compression process, the value 2ln by 60. If it is single stage, that will be ln by 60. If it is two stage, 2ln by 60. So 2ln by 60 is equal to 3 meter per second. From that equations, you can calculate, you already know the value of n, that's the speed that is given in the numerical as 250 rpm. So from that expression, you can calculate the value of L, that means stroke. Stroke is your 36 centimeter. Okay, 36 centimeter. Now, in the next part of the numerical, you have to calculate the diameter or bore. Okay. Now, when you calculate the bore, as we know that volumetric efficiency. What is volumetric efficiency? Now, volumetric efficiency is the ratio, or it is defined as the volume of air intake in per cycle divided by stroke volume of the cylinder. Okay, it is the ratio volume of air taken in per cycle divided by stroke volume of the cylinder. Now, actually volume air taken in per cycle, okay, volume of air taken in per cycle, that will be because of 4 meter cube per minute divided by the number of speed, that is 250 rpm, is equal to NV, volumetric efficiency, into stroke volume of the cylinder. This is the stroke volume of the cylinder, pi by 4 into d for the low pressure, because in two-stage compression process, one is low pressure, one is high pressure. First of all, we calculate that for the low pressure, okay, low pressure compression process or low pressure cylinder. Now, so total actually volume of air taken in per cycle, that will be 4 by 250, that equal to volumetric efficiency into stroke volume of the cylinder. This is the stroke volume of the cylinder. As the L is equal to H, as you know that L is equal to 0.36 centimeter, and we can assume that here L is equal to H, means height is equal to length of the stroke. Okay, here, so volumetric efficiency into pi by 4 into d into L dLp the whole square into H, so 0.36 here. So from that expression you can calculate, because volumetric efficiency, value of volumetric efficiency is given, that is 75%, I think in the numerical is given. Now all these terms is known to you, that from that expression you can calculate the diameter of the low pressure in case of low pressure cylinder. Okay, this is the bore. So 0.266 meter, that will be is converted into 26.6 centimeter. Okay, now you have to calculate the diameter of the high pressure cylinder. How do you calculate? As we know that for the intercooling process, there are three lines, P1, P2, sorry, is the P1, P2 and P3 line. The expression that T1 is equal to that was 1, okay, so that is 1, that is 3, so T1 is equal to T3. Now for the compression process, P1 V1 by T1 is equal to P3 V3 by T3. So as it is constant pressure process, T1 is equal to T3. Ultimately the expression was V3 by V1 is equal to P1 by P3. V3 is nothing but the volume of the high pressure cylinder, that will be pi by 4 into d square into L, and V1 is nothing but is the low pressure cylinder volume, so pi by 4 into d square into L, so d will be dLp here, and d is here dHp, means high pressure cylinder. Okay, that equal to P by P3. So value of P1 is given, that is 1.013 divided by P3, that is 9 bar. So the 9 is given. So from that expression you can calculate the diameter of the high pressure cylinder, or diameter or bore of the cylinder. The expression, the final answer will be 0.892 after calculating all the numericals, 0.892 meter. If you convert into centimeter, the expression will be ultimately the final answer will be 8.92 centimeter. Okay. So thank you very much. Good night.